Welcome back from the coffee break. We're starting the fourth session, Outreach and Creative Destruction of Medicine. We have 4 very interesting talks lined up about swarm learning, about counterfactual GANs, and about myths in genetics of South Africa, and more about that. First, we start with Matthias Becker from DZNE Germany about how to build a good swarm learning experiment, or swarm experiment.
Looks great. All right, so good morning, everybody. I realized just during the coffee break after handing in my slides that I picked the wrong title. I should have checked the agenda and clearly should have called it Swarm to Gene. So bear with me during the day. So we've seen a high interest in artificial intelligence. We've seen very interesting applications this morning, and there was this common pattern of I don't have a lot of data, I don't have enough data, I have to apply other technologies. And today I want to talk to you about how to set up a good swarm experiment. So last year in this meeting, Joachim Schulze introduced swarm learning to you. I will do a quick recap of that. But after this and after our publication in Nature, we received a lot of feedback, many people that wanted to start with swarm. So I thought today would be a good opportunity to show you how to get started, what are the first steps needed, and yeah, basically how to set up a good swarm experiment. Quick show of hands who is familiar with swarm learning. There's a number of hands missing, so I will do a quick introduction. So swarm learning is a variant of federated machine learning. You train local models at different sites on local data, and then you merge these models in a regular interval. In comparison to other federated technologies, in swarm learning, you don't have a central player. So this merging process is done by different nodes each time, and therefore you don't have one single instance that controls the model. So the important part is you don't have a central player and you don't have to give away your data. So your local training data always stays local. This allows you to collaborate even in scenarios where privacy concerns would not permit that otherwise. We have shown that very successful on transcriptomics data. So here, this is our example from the decoy study where we had a COVID-19 data set that we trained on 6 different sites. And after publishing that, people already picked that quite fast up. So just a few months after us, the Carter lab in Aachen published a preprint at that time that was on cancer histopathology. And there they were working with imaging data. So you could already see that the method and the approach can be easily transferred. They were using 3 different data sets from 3 different countries and basically could produce similar results. And I'm very happy that they were able to get their preprint finally into Nature Medicine earlier this year. We are also working with other people within Helmholtz. So this is one example driven by Maren from the systems medicine, together with the people in Helmholtz Munich at the ICB and at Helmholtz AI, where we basically have shown that integration technologies for single-cell data sets can also be applied to swarm learning. So we were running an integration experiment with data sets in Bonn and in Munich, and we could see that this works very successful. There's a number of other publications. It has been shown in tumor segmentation. There have been cases in robotics, and there have been a lot of discussions how do these privacy-preserving technologies work, what are their alternatives, and yeah, in general, it has been perceived quite well. So what I want to do today is I want to talk to you on how to get started on these swarm experiments. So since we are inside, I've picked this nice picture from the forest. You can see a way going to the left. It is very wide. You don't have any steep hills or so. So this is a very common way. On the right, you see a small path that's going up somewhere, not really sure where. And today we want to explore both paths. So on the left, you have the easy way. There's an existing swarm experiment that you want to join because you have data. We will talk about that. On the right, you see the part where you need to put in some work. This basically means how do I start my own experiment. And this is what we want to discuss first. It will take some time, but afterwards you will see that just joining, if you have a data set, will be even more easy. So how do you set up your own swarm environment? Well, you have to go through a number of steps that we will discuss in detail now. This is about the question that you want to answer, the model that you have, the data, the pre-processing of the data, what are the hardware requirements, how do you turn your model into a swarm model, how do you start it, how do you stop it, how do you evaluate it. So let's start with the most obvious one. So the question and the model. Obviously, you need to ask a question that can be answered by machine learning. And this has to be a question that you can already answer with your local data, but maybe not as well. So if you have a question or a model that does not work on your data, it is unlikely that it will work on the swarm because it needs to work on at least a little bit on every single node. So you need to have your question that you want to answer, and you need to have a prepared and tested model. Then you can go ahead and say, I want to talk about data. So you have a data type in mind. These could be the scans of the X-rays of bones. These could be gene expression information. These could be full body MRIs. These could be photographs. This is basically unlimited what kind of data type you have. But if you're setting up an experiment, you want to decide very early on what are the standards, what are the requirements for your data sets. So you want to agree on aspects like for example, what nomenclature you use for naming of genes, what references do you use, what is the requirements on what data types do you include, what don't you include. So for example, if you have a series of images, what is the bounding box, what are the requirements for that? And certainly you want to define a minimal quality of your data set. So if you have partners that contribute very poor data to your swarm, this is something you would like to avoid. So once you have decided on what kind of data you want and how this data should look like, we can talk about the pre-processing. In the pre-processing step, you basically want to say, how do I normalize my data? How do I bring it into a common format that can then finally be fed into the model? Here you can think about, if you work with image data, turning it into smaller blocks, and these needs to be standardized. You can think about corrections if you have uneven lighting in a photograph, for example, or in microscopy, if you have some artifacts. You basically define how do you want to remove that, how do you want the data that goes into your model to look like. And here, after defining the steps, you set up a script that can be applied to the data, and then this should be taken up by everybody else as well. So let's talk a little bit about hardware. I mean, these steps that we've discussed so far, they can be done locally. That can be, this is typically a straightforward process. And here we need to separate two parts. On the left side, you see the training hardware. Here, it really depends on your model. If you do a super complex natural language processing model that needs to be trained on dozens of GPUs, then of course this is a requirement for you. But many models are often a lot more simpler and probably don't have these requirements. For the swarm itself, there's a number of requirements. It runs on regular servers with typical configurations, I would say. These nodes within a swarm need to be able to communicate with each other. So this can be quite challenging if you think about a hospital environment. However, I think this is still a solvable issue. With the swarm learning framework, you have the guarantee that all communication is encrypted and authenticated to the other sides. This is this SPIFFE-SPIRE protocol that is used there. And if you are approached about, but what about traffic? We don't have a strong internet connection. This is again a topic that depends on the model that you're using. If you have a small model with just a few hundred parameters, then you have to say, then you can think that the synchronization only contains these parameters. And if you are the merging node, then you collect all these parameters for your other swarm nodes. But this is still not a lot of data. If you have a super large model, something in the transformer size or even beyond that, where model parameters are in the gigabyte range, of course, network traffic is becoming more of an issue. The whole system is Dockerized, so it does not make any permanent changes to your environment. And of course, you need the swarm learning software. So now we have our model. So this is a super minimal example that you can see here. And the parts that are in bold text are the additions that are needed to turn this into a swarm model. Yeah, I'm not sure, some of you might have already recognized that from the input shape, 28 by 28, this is actually taken from the MNIST numbers example. So this is just super minimal. So you will need to import the swarm callback so that you can access the swarm library. You need to define on how many epochs you want to train, how many partners you want to have. And then it's basically just, you can see on the right side, defining a callback. And then in the end, when you do the fitting of your model, you set this as one of the callbacks. Of course, you can have your other callbacks if you want to do some logging or some intermediate results reporting there as well. So once you have made these modifications to your model, you're ready to start the swarm. Starting the swarm is basically a two-phase process. First of all, you need to set up the first node. The first node is called the Sentinel. It's like every other node. The only difference is there's no blockchain yet, so it's the one that is initializing it. Afterwards, it acts like a normal one. Then you join your machine learning node, and you are ready to start training once the starting conditions are met. Now comes the fun part. You pick up the phone, you call your colleagues, and you encourage them to join your swarm, setting this up. And then once you have met the start criteria, the swarm starts the training. So there's just one formal requirement to actually start. This is the minimum number of participants. So once you have this, the swarm actually starts. Here you can be a bit careful. So if you have partners of different sizes, if you have a minimum number of 2 partners and these are very small partners, you might want to wait for a larger one to join as well. But this is optional. So now your model is training, you are happy, you are eagerly awaiting the results, and how does it stop? So there are 2 end conditions for the swarm to stop training. First of all, there's a number of epochs that you have defined before. Once this end is reached, training will automatically stop. The other one is if your start conditions are no longer met. So if you require a minimum of 3 participants in your swarm and you drop down to 2, then the swarm will also stop training until this requirement is fulfilled again. On the right side, you can see a nice scenario described on the top that deals with different sizes of data sets. So this is again from the Carter lab. They looked into this quite nicely because if you think about training your model and are looking into stopping conditions, if you have different sizes of data sets, some sites might train faster than others. And they have looked into how to continue training the swarm even if you have already processed all your data. And they've shown that if you repeat training on existing samples to stay along with the swarm, this can increase the performance. There are some other considerations that you should take when looking at the end of the training of the swarm. So first of all, there's a risk of overfitting. However, since you work in a swarm, you're not always training on your samples, but after each merging step, you're also getting input from other samples. So this risk can be mitigated by the swarm. If you decide to go for a very long runtime, you might run into issues through continuous training. So imagine you have a swarm with 20 participants that is designed to run for a very long time, and the first 10 participants have a very specific data set, and they leave after a while. They just drop out of the swarm, and then new participants come, and we run into something that we call concept drift. So this basically means we get new data sets, we get new concepts in these data sets, and the overall training of the swarm might forget something that was in the old data that is no longer present. So here it makes sense if you have diversified data that is changing over time to make sure that over the whole runtime of the swarm, especially towards the end, your diversity in the data is still present. The final point about the training. So it's nice to train your model for a long time and maybe wait for new data to arrive, but we have to talk about energy consumption. So this is not only a recent issue, but recently it has become much more important. Training a model takes a lot of energy. There are two things you can do, or there's a number of things you can do. So first of all, minimize the training time that you need. Maybe you want to start with a pre-trained model like we've seen before, so you can already just do transfer learning. You can also say, I want to sparsify my model. So if you already have experience with a model class, you might want to reduce the number of parameters that you need to train. And this is crucial because there's not only the topic of energy consumption, but also directly related to that, the CO2 emissions. I recently discussed with a colleague from KIT, and they have a very sophisticated GPU cluster there where they train a lot of models, and in their systems they have dedicated hardware that measures the energy that is being consumed during the training. And when you submit a training job there, at the end you get a report about the energy that you've consumed. And at the same time I learned that a medium-sized language processing model can cost as much CO2 emissions as a car over its whole lifetime. So building it, driving it, and this is quite a lot. And at the same time, I also learned that most of the larger German data centers run on rather dirty energy sources. So there's a lot of coal, electricity in there. So keep the energy consumptions of your model in mind when you design, when you train. So at the end, what do? You want to see results. There are two approaches that we can go. First of all, we can do node level evaluation. So basically we have a test train split on each individual node, and there we can collect the common metrics. So we can go for specificity, sensitivity, you name it. We can also do an evaluation on the whole swarm. So we could have different scenarios. In the beginning, the decoy example I showed you, there we had two holdout nodes. So these were two nodes with data sets that were not used for training, but simply for evaluation. You can also say I collect data sets from, or part of the data set from every node and then do the evaluation on that one. Although this might require some data sharing that can be complicated. And lastly, of course, you can aggregate the node level statistics. Just a quick comment on the legal side of things. Of course, when you join a swarm, you sign a collaboration agreement. This is intrinsic to the swarm. Here you just want to outline how do you want to collaborate. You might want to put some phrases on ethics requirements in there, and you want to define a goal for your collaboration. The good thing about swarm learning is, since you're not sharing any data, you don't have to worry about data transfer agreements or joint controller agreements. However, think about IP for the models that you create in advance. So these are the steps to set up the swarm experiment. I think it's not too complicated, but if you want to join a swarm, this can be even easier. So now we take the easy way. This is the large path traveled by most. First step, find a swarm experiment that you want to join, agree to the conditions. So if you know that, for example, Peter is working on a swarm experiment and you have data that is interesting, just call him and ask him, hey, is there something that we can collaborate on? And he might have something, or he's already reaching out to you. And yeah, the same applies to the data. So here, you no longer set the standards, but you have to follow the standards. So just you get a set of rules, how should your data look like, and then you get a script, how should I pre-process my data, and this is the things that you need to apply. Now, since every node in the swarm can be the one doing the merging from time to time, you can see that there's actually no difference in the requirements. So every node has the same basic requirements, and the biggest factor of it all, again, is on the left side, the training hardware. So really the resources required to train your model. And this is already it if you want to join an experiment. But how does this work on the technical side of things? So I did a deep dive into the documentation, and you can see here just two diagrams. On the left, you see a generic description. On the right side, you see a simple experiment with two nodes collaborating in a small example project. And you can see there's a number of nodes involved. If I I will not go through all of them. There are swarm nodes, there are swarm learning nodes, there are things for coordinating. This is a very powerful system that allows you to set up very flexible configurations and is something that can be scaled across very different environments. But I can see clearly that if you want to go into a clinical environment with such a setup, that this is not the way to go. But instead, I want to show you something today that we call the ImmunoHub, and this is a project that we did in the COVIM network. COVIM is one of the NUM projects that is focusing on COVID immunity, and here we have built a data management and analysis platform that uses swarm learning. In the ImmunoHub is something that will be installed at your local hospital. There you can securely store your data of different data types. You can have metadata, you can edit it, search it, and so on. You have the possibility to share with colleagues in your same hospital. So typically this is covered by ethics and agreements. So you can work on the same data as your colleagues if they share that with you. You can do R and Python data analysis. Basically, there's a Jupyter notebook running, and there you can process your data, visualize it. And if you want to collaborate with partners in other places, like if I want to do a collaboration with our partners in Aachen, for example, sharing the data becomes suddenly more complicated. So here, swarm learning comes into play. So the different nodes of the ImmunoHub are connected by swarm learning, and I could then advertise my data set, my analysis, and do a swarm experiment together with my colleagues in Aachen so that we can collaborate without actually sharing the data. Technically, it looks a little bit like that. So in the middle, you can see the different ImmunoHubs installed at the different sites. Here, each hub has their own local set of data. And you can see on the top, there's something that is called the central ImmunoHub. This is basically a marketplace for data sets and swarm experiments. So if you have set up a nice swarm experiment, you can advertise it there and look for participants, or if you have a nice data set, you can also advertise it. For data sets, obviously, you're only publishing metadata there and nothing that is personally identifiable information. On the bottom side, you can see that all these nodes are also connected through swarm nodes so that they can collaborate if you want to run a swarm experiment. In total, this platform looks like that. So you have a nice login screen. It tells you about your latest experiments. It gives you some statistics about the platform, what has been happening recently. And then you can just take a look at your data sets. You will find some information on when you uploaded it, what it looks like. When you upload it, you can select the data types. So for example, here we added support for flow cytometry data. You just upload your data set. It will run some basic analysis on it. It will extract the metadata, like for example, the channels that you have measured in your experiment. And then afterwards, you can go ahead and present your data set. Now, you can also do a swarm experiment. The interface looks quite similar, so you just say that you want to join a swarm experiment. Here you can see that we are asking for the same parameters that I told you before, so the number of participants, the number of epochs, and so on. When we do that, we also have to modify our code, and highlighted in yellow, you will see the exact same modifications that I showed you earlier to swarmify your model. Maybe just a quick word. Once you have developed your successful model, I just wanted to quickly highlight two trends and regulations. So in the US, there's this new software as a medical device ruling. This gives already quite a good guideline to the FDA on how to allow AI applications in medical scenarios. In Europe and in Germany, sorry, I couldn't get an English version of that text. It was too legal. It's a bit more complicated right now. AI applications are still considered quite risky and require a lot of quality assurance. However, there are a lot of discussions currently going on, and if you run into a politician, encourage them to simplify that. So lastly, I want to tell you briefly about some of the activities that my group is currently working on. So we are currently evaluating the behavior of the swarm in stranger conditions. So we already took a look at how imbalanced nodes work. So if you have very large and very small nodes, this typically is performing quite well. It can have some effects on the training and merging, as I showed you before from the Carter lab. If you have very different swarm nodes from each other, you might have to do some weighting during the merging, but this seems to work quite well. What we also want to investigate is bad quality nodes. So how does it work if you have a partner in the swarm that is having data that doesn't really fit the quality standards that you were expecting? Typically, there's a small number of nodes with bad quality. During the merging process, they get good parameters from the nodes with better data, and this evens out. However, we're currently studying where this tipping point is. So how bad can the data in a swarm get before the whole swarm performance goes down? And lastly, we're interested in malicious nodes. So what happens if a node, well, maybe not malicious in the first place, maybe they just have an error in their results. So they are reporting, they have switched up true and false on some labels. But there could be also a level of misbehavior where they report false or random results. And again, there we're also looking into that one. And this already takes me to my conclusion. Joining a swarm experiment is easy. Setting up one takes a little overhead, and we believe that the ImmunoHub that we have built is a good tool to make swarm learning easier to use. Lastly, I just want to mention that we're on the lookout for PhD students interested in AI, ML. We're building clinical decision support systems, are looking into explainable AI, multi-omics. Please reach out to me. These are our partners, Swarm Learning. We work a lot in Coven with Commasoft and HPE, and the Systems Medicine Group at DZNE. Thank you very much.
Great talk. Are there any questions? I believe in the front, Nicolas.
Yeah. It's really interesting swarm learning. I'm learning a lot about this in this conference. Like, I think the challenge for me, and I think a lot of researchers, is these collaboration agreements and so on, and getting lawyers to understand what you're doing and that it's safe and that you know, you just want to share data and get on with work. So do you have, like, I don't know, how involved do you get in, you know, convincing these people higher up, you know, decision makers that, you know, this is an approach that we can go for? Do you have templates or something, or a contact person?
We don't have templates, but from discussions with the data privacy officers, typically when we explain to them, we are only sharing the parameters, the models, not the real data. This already helps a lot.
So it's easy, is what you're saying?
I'm not making any promises.
I wish to ask a simple question. Where does a net benefit, where does a true gain comes from? Well, we are talking here about genetic diagnostics. And involved in that, I recognize that the field is working almost with identical methods, identical algorithms, no proprietary methods, because it is much too complicated. There are none. And they are using identical databases. So that appears to me that is sheer redundancy. And I can't see a reason how to gain a net benefit from starting a swarm in that situation with molecular genetic diagnostics, which a priori seems to be a good application. It might be even worse, and one of your slides addressed that. If there is one highly competent center of using all these resources, and the other are close to incompetent, then the the resulting or the overall result may be worse even. At least I could imagine that. That comes up to the German saying, and I can't say that in English, der Stärkste ist am mächtigsten allein. How would you answer that question?
That's an interesting point. So, yeah, just following up with my previous speaker's first disclaimer, I'm a computer scientist, so my domain knowledge is limited to a certain degree. However, if we look into machine learning applications, there are tons of paper that tell you get better performance if you have more data. This might not necessarily be the case for one single strong player that doesn't want to collaborate. But if you think about smaller groups, if they team up through swarm learning, they have access indirectly to more data, and therefore they can build more robust models that can do predictions with a higher accuracy.
May I add, if you allow, Matthias? Thomas, this is, if you take gene diagnostic on the genome level and that's it, maybe you're right. But genomics and genomic diagnostics goes far beyond that now. So we're not talking about databases anymore. We're talking about functional genomics data that have to be brought into the diagnostics. If you think about chronic diseases like we heard from Johanna, the genome will be one part, but then there's the transcriptome, the epigenome, and so on. And the machine learning algorithms on those require much larger data sets that any kind of center in the world can actually have. We talked with the Broad Institute, with Genentech. They all have the same problem. Not enough data access to these functional genomics data. The only way to solve that problem is to work in large networks together to get anything out there. Is completely different to the databases that you have been used in the genetics diagnostics. That's the future. And I think we need to get these people together. And one way we thought for a long time the cancer field is to push everything into one place. And you can ask the cancer people how painful that is, and it still is. Yeah? If you ask the German cancer biologists how difficult it is to contribute to international consortia because they cannot give their data to the US, that's not the way forward. Yeah? So we need to have these decentralized versions. And how it looks in the end, whether it's this one or another one, we will see. But this is going beyond classical genetic testing.
Well, I got the message, Joachim. I will think it over.
We are out of time.
But at the first glance, it looks like as a philosopher's stone.
I think we can continue this after the sessions are over. Seems like a very interesting discussion. Thank you very much again for your lovely talk. Next up, normally we would have Sylvan Mertes from the Human-Centered Artificial Intelligence from Augsburg. But we have a sub, which is the colleague Fabio Hellmann. He will be telling us about explainable AI by counterfactual GANs. Please.
Thank you. Okay, thank you very much for the kind introduction. And thank you for inviting me to this conference. It has been very interesting so far. Yeah, so let me first introduce myself a little bit. My name is Fabio Hellmann, and I'm working at the chair of Human-Centered Artificial Intelligence, which is located at the University in Augsburg. At our chair, we mostly do work on social robotics and computational teaching systems, social signal interpretation, but also explainable AI. We have heard quite a lot of really interesting talks about what AI can do and how it can help us to improve our research, but also the clinicians in their daily life. Explainable AI, or short XAI, is what I'm going to talk about today. But in particular about counterfactual explanations. First of all, let me give you a short motivation for it. I think we quite heard quite a lot of talks about the AI and what we can do with it, and that it gets even more and more in practical use in the clinics, even if it's commercial or non-commercial. And the one point that we, I guess, can all agree on is that we definitely need something to explain those models that we use, because otherwise we just need to trust them blindly, and we don't want to do it. So, current state of the art AI algorithms are usually also called black boxes. Why are they called black boxes? Because we can't really look into them. What are they doing? How are they coming to their decisions? And so on and so forth. Of course, these decisions need to be made visible to us, and that's kind of difficult because machines work differently than we humans do, and that's the place where we want to step in. What I also want to mention is that with AI products, we don't want to replace anyone in the work field, not physicians or anyone else, but we want to support them. And if we want to support them, we need them to understand what we're doing. So a good example is, I think every one of you have heard of COVID, and every one of you have heard about the analyzing COVID lung X-rays. And if they want to decide or classify if a lung has severe COVID or not severe COVID. And therefore, usually the AI just predicts the lung you see has COVID or the lung does not have COVID. But now it's up to you as a physician to interpret these results. Usually when you as a physician say, yes, this prediction is in alignment with my decision, then it's totally fine. But what if you say this patient has COVID and the AI says otherwise? Then of course you have to find out why those decisions differ from one another. And there comes in the different XAI paradigms. First of all, we have the feature attribution, which helps you, like we have seen in previous talks, for example, in the bone talk, bone to gene, where you've seen the X-ray images of hands, where you could see the bones, and also these called saliency maps, or also called heat maps, where you could see which region was relevant to the AI to make or to come to this specific decision. On the other hand, we have counterfactual thinking. This is more like we humans explain to other humans how we explain our decisions. So it's more like a what if, not a which question. So yeah, I will present you some examples shortly. But first, let me show you some examples for the feature attribution, because also for the feature attribution algorithms, you can differ between local and global algorithms. When you want to see what specific regions or decisions for a decision were relevant to the AI, you want to look at local explanations. But if you want to get an overall grasp of the whole AI, what was relevant for the whole AI, you want to look at the global explanation. Here's an example of lung X-ray, whether it has pneumonia or not. We don't know. We trained an ML classifier to help us with the decision, and the ML classifier in this case stated, I predict pneumonia. So now we have the prediction, but how can we see why does the ML classifier come to this decision? Then we can use those feature attribution algorithms to run it on this image and the classification, and it would highlight the green area. So the greener the pixels become, the more relevant it becomes for the decision making. So on the contrary, we have the counterfactual thinking of the what if question. So what if the input would look different? Or what if the AI had made a different decision? To give you just a simple explanation or a simple example, if you were asked, why don't you like your job? You probably won't answer, my boss highly contributes to me not liking my job. But you would rather say, I would like my job if my boss was not so demanding. Such an answer shows you an alternative reality. So a reality where the decision would have been different from the one that has been made. And that's exactly what counterfactual thinking does, and how it's comparable from the human-to-human explanations. To give you also an overview of the different explanation types that are in the counterfactual thinking, first of all, we have the factual explanations, which I showed you before, which are just other input result in the same decision. So you put in, for example, another image of pneumonia, and still pneumonia comes out, but you still don't know why it's pneumonia. Counterfactual explanation, on the other hand, how would the input have to change in order to change the decision, would have to change the input image so that the decision threshold has been met to change to the other decision. The semi-factual explanation, even if the input would look like this, the decision would still not change. So this means even if the image has been changed, so modified how it looks, the decision threshold would still have not been met to overcome to become the other decision. And counterfactual explanations, which has been invented by our chair recently, says no matter how certain aspects of the input change, the decision would always be the same. So it just alterates the completely irrelevant features. So you see basically afterwards which of the features do not contribute at all to the decision making, but it doesn't really give you a hint what could have or should have been changed to alter the decision. So to make it more illustrated, here's a simple graph. We have the origin as the star here. This is our basic input, and with a factual explanation, which is right next to it, it's basically another input giving the same decision. The counterfactual, as I mentioned just before, alterates all the different features that we have on the scale that nothing else changes, so we stay on the same level. The semi-factual explanations, on the other hand, then goes up to the threshold, but just stays below. So we still have the same decision to keep in class X and don't change to class Y. And now, on the final note, the counterfactual explanation then changes the original image to become just above the threshold, so it changes from class X to class Y, and that's what we're looking for. To give you a very simple example of how this might work, we have a cactus that we want to keep alive, and we have two features, the temperature and the weather. Originally, the cactus might die because the temperature is of -5 degrees and the weather is sunny. So how can we figure out to keep our cactus alive? We can use the factual explanations, which gives us different examples of still the same result. So if, for example, we change the temperature to -13 degrees and the weather is rainy, and we see the decision is still the cactus dies. When we take a look at the counterfactual explanation, the temperature rises to +5 degrees, the weather stays sunny, and the cactus suddenly stays alive. So that's what we're looking for. But on the other hand, the semi-factual thinking just changes right below the threshold so that we can see still by +4 degrees and sunny, our cactus even would die. And the counterfactual thinking just changes all the non-contributional features, in this case, the weather. So the temperature remains the same, but the weather changes to rainy and we still have a dying cactus. Okay, but how can we apply this to our medical domain now? We have in the counterfactual explanations, it makes it very simple if we just have numerical numbers. But of course, we want to analyze images because we mostly have images. And that's what I want to focus on right now. So here in this example, we have microscopic sections, skin images, facial phenotype images, and X-rays. But how can we construct from these images counterfactual explanations? So images that are still based on this original image, but show a different version of it where the decision is changed. Here comes in what we've heard in the previous talk, the counterfactual explanations with GANs, or generative adversarial networks. To give you a short introduction of what GANs are for and how they are used, GANs exist out of two networks. So we have a generator, which uses as an input random noise, and tries to generate images that look very realistic. And on the other side, we have a discriminator who tries to identify if the generated image was fake or a real image. So they compete against each other, and by competing against each other, they improve during the training process. The fake images improve and look more and more realistic, and that's the basic idea behind the generative adversarial networks. So, but I just told you that we want to change the original image to still look like the original image, but has some modifications that the decision boundary changes. So with this just generative adversarial networks approach, we can't do it because we generate completely new images based on random noise. So there comes in some alterations for GANs because there have been some developments in also different directions, style GANs and also cycle GANs. And even more, I think we heard about style GANs in the previous talks as well. Counterfactual explanations try to use those cycle GANs where you, no, this one, where you don't take in random noise to generate new data, like in the original GAN approach, but to take two data domains, domain A and domain B. For example, if we look at the pneumonia case, we take the lung X-rays of pneumonia as domain A and lung X-rays of healthy lungs in domain B, and then we train the GANs with each other to reproduce the results. But if we just use this approach, it might not work because we don't have our classifier put into the loop who can still tell us if the decision threshold is reached or not. So we modified the architecture a little bit, and I don't want to go too much into detail, but here you can see we put the classifier in the middle of the communication. So the generator always puts in the output, so the generated image of one generator goes in as the input for the other generator and vice versa. And as such, always tries to predict with the classifier if the prediction has been changed or not. And with such an approach, we then can generate images that are based on the original, but slightly modified to produce a different decision. Here we have another example with the pneumonia X-rays. On the upper row, you see that on the left side, the healthy image, and on the right-hand side, the counterfactual explanation, what the lung might look like if it had pneumonia. And in the bottom row, you see that pneumonia as the original image, and with the counterfactual explanation, it becomes a healthy lung. So you can see that in the previous feature attribution explanation, you could see only the green dots, if you can remember it. So which section or pixels were relevant to the decision. But now you can also see that the opacity of the lung might also be an indicator, which you couldn't see before just with the green dots. Like here, it's very clear that the lung looks more clearer than before. And before it was only some green dots in this region, which couldn't tell you much about it, what the decision was about. And also, if we look at some other examples, we run it with skin lesions, to be more precisely with melanoma and melanocytic nevi. And again, on the upper row, you see the original image, and on the row below, you see the counterfactual image. And here you can see very clearly that also the color somewhat contributes to the decision, what can't be seen in a feature attribution explanation, because there you only see the pixels that are relevant, not the color. So, for example, the melanocytic nevi was mostly predicted when the image had a reddish color. On the other hand, the melanoma was predicted when it was pale skin. So the paleness also indicates somewhat of the bias of the neural network, because even if the skin is not pale, we might assume that it can be a melanoma. Yeah, to sum up my presentation, I showed you the counterfactual explanations and how it can be used and what it creates, and also some of the examples that we have explored so far. And we are currently working also on using the counterfactual explanations on the Gestalt match database, but we don't have any results yet to show. And last but not least, I want to encourage you, if you have any idea now where we can also use the counterfactual explanations in your research case, we would be very happy if you get in contact with us. There are our email addresses, but you can also talk to me later, and then we can talk about it. Thank you very much.
Thank you very much for your interesting talk. So if I understand correctly, do you basically create qualitative examples to what clinicians or experts can compare the healthy and non-healthy images to?
Yeah, so the images are always based on the original image that the doctor puts into the algorithm. And afterwards, if it's an infected lung, a healthy lung comes out, and if you compare those images, you can see just by looking at it the differences in the image, if it's the opacity, the color, or some regions, which could also be highlighted by the feature attribution algorithms, but it's more on a deeper level with the counterfactual explanations.
So this would also tell you something, or could tell you something about possible biases of the model then?
Yes, of course.
Cool, cool. Any other questions? We need some cubes.
Yeah, so I'm interested in this area, and yeah, maybe we can talk about applying this as well to our data. So we haven't been very successful with saliency maps. Maybe we're not doing it right, I don't know. Counterfactuals could be interesting. Depends, I guess, how different they are from the original image. I mean, I don't know. Is it the problem with saliency and attribution maps is you highlight some pixels, you don't really know how to interpret it. It's not obvious sometimes. Do you think you have the same problem sometimes with the counterfactuals? If it shows you a completely different image, for example, that wouldn't be very helpful. I guess the image needs to be slightly different. You need to be able to.
I would say, of course, it's always up to the interpretation of whatever explanations you use, because each explanation has its advantages and disadvantages. But I think counterfactual explanations have a huge advantage over the feature attribution algorithms because of the more in-depth information that you can get out of it.
Okay, thank you. I saw another question in the back. Alexei, if you could pass on the... Oh, never mind. It's very useful, this.
Okay. Yeah, thank you. This is very interesting. My question would be, so basically you're trying to convince someone who looks at an image and who's very familiar with these kind of images what the reason for this decision was. We often work with data that is non-image based and so high dimensional that not even we always know the explanation, even if we see it. Mm-hmm. So let's say gene expression data has tens of thousands of dimensions. Even if someone were to highlight for me, or in this case the AI, this is what I based my decision on, it's only meaningful in a limited way. Have you been thinking about how you could expand this idea to actually give more information? So not just if I change these 3 genes, then I would have changed my mind, but actually it's because it's always in correlation with this one, or like to build up on this for cases where it's not visual inspection of an expert.
So you mean basically the dependencies in between values of the genome?
Yeah, like if the truth is not known, if I am familiar with lung x-rays and I see, there's this opacity, you show me if I reduce it, then I change my mind, yeah, makes sense. But for all the genes, nobody can possibly know how they all interact together, so there is no known truth, if you will. You know what I mean? Mm-hmm.
Yeah. So it's a very interesting question. It's difficult to answer because the cycle GAN that I showed you before also needs some data to train from both domains. So if you have only one domain, the alterated or the ground truth basically, and you don't know what else can happen, so you only have one domain, it might not work. And also you need some kind of classifier in between to train those models. Otherwise it's also not going to work.
I mean, I think it could work because you have so much different transcriptomic data, for example, that you could have different domains, like different conditions, for example, and you could have a classifier that classifies those conditions. However, it's still not obvious why the decision has been made. I mean, this is a very complicated question. I just wondered if you had been thinking about this at all.
Yeah, we have mostly focused on images so far. Okay. So we can definitely talk about it later if the numerical values are also interesting.
Yeah, okay, thank you.
One more question in the front. Watch out, there's a cube.
Discovery, I guess, is, I think, a word I think a lot about when it comes to AI. Like, we're not really discovering new features. Well, yeah, I just wanted... it's not really a question, but yeah, we can discuss it later.
Yeah.
Right, I think it's really important, yeah.
Yeah.
Like, yeah, basically.
So we have time for one more question. Peter in the front.
Yeah, often when we are presented with theories that we are asked to continue, we build a hypothesis and make suggestions that would confirm this hypothesis, but you are actually quicker when you try to falsify your hypothesis, right? So I wonder, what does the counterfactual network actually do? Does it also try to falsify its features?
It's not really trying to falsify its features because when you look at the training process where you have the cycle GANs training each other basically and having the classifier in the middle, you don't really try to falsify values, but you try to figure out the threshold of the already trained classifier. which says you if the decision is above or below the threshold in one or the other domain. Yeah.
Right, thanks again to our speaker. And next up, we come to the outreach part of the session. We have Shahida Moosa from Stellenbosch University in South Africa. And she will be talking to us about the genetics in Africa, myths, challenges, and triumphs.
Thank you very much for the invitation and the opportunity to speak here today. Let's see if I can get this up and running. We are changing gears completely. Not much talk about the blockchain or GANs or AI. We're very much flying over the Mediterranean and entering into a new continent. And I'm excited to talk to you about some of the myths, challenges, and triumphs that we've encountered on our journey to be able to implement genomics in Africa. And I've chosen that particular genomics in Africa because I think we should start with one of those myths, that Africa is somehow a monolith, something that's very homogeneous. There are more than 1.4 billion people that live on the continent in 54 different countries, a couple of disputed territories. And if you can just take South Africa as an example, we have 11 official languages. Can you imagine how many unofficial languages there are? So the continent is extremely diverse with regards to people, cultures, languages, ethnicities, religions, etc. And so just talking about Africa as one thing that, Africa equals Africa equals Africa is very misleading. We're all very familiar with the out of Africa migration. So many thousands of years ago, the first humans left Africa, took some of the diversity that was available on the continent with them, and ended up in the farthest regions of the globe. So while Rudolf and I are probably the only two that were born on the continent, I suggest that everybody in the room and listening online is also African. And so I'm taking, if you trace back far enough, you'd find your ancestor in Africa. So I take this opportunity to invite you to attend the International Congress of Human Genetics in Cape Town next year. It's the most beautiful city ever. That's my home. And the theme is coming home. So we're waiting to welcome all of you as Africans back to Africa. Right. This is one of my favorite photos. I took it off Google Images, the collage of different faces from across the continent. And it doesn't matter if you're interested in art or language or whether you're Tsung and you want to look at facial images. As a geneticist, all of us are really interested in the diversity and exploring the diversity that underlies this diversity in the genetic basis of the diversity on the continent. And that exact diversity is mirrored in my clinic. These are a few images of children that I've seen in the pediatric genetics clinic. And we are very interested in trying to find out. We think that they all may have a rare disease. And I think that we might have some ideas just looking at the faces there. Gestalt Matcher might have more ideas as to what's going on. But we need to really be able to put in place all the resources and everything that we need in order to tackle this problem. And these patients all, like I said, all have what we call rare diseases. We follow the European definition of less than 1 in 2,000 people affected by the condition. They used to be called orphan conditions also in Europe. That's changed a little bit. It's still very much in Africa, so I can generalize sometimes. There hasn't been much input, much prioritization for people with rare diseases across the continent. And if you think about how many thousands of diseases we're talking about and the number that grows every day, this is cumulatively quite a big proportion of the population that may be affected. And we're talking in numbers about 300 million across the world. We estimate about 3.7 million in South Africa. We don't exactly know because most of them are still undiagnosed. And if you can think of somebody, you have a child, there's a problem. Like TJ was saying yesterday, he went from doctor to doctor looking for an answer. If you're lucky enough to be born in Rady's Children's Hospital in California, your diagnostic odyssey is 13.5 hours. If you were born in South Africa, it's maybe at best 4 months. If you're born in the rest of Africa, you'll be on your diagnostic odyssey for the rest of your life. And so this is something that we need to take very seriously, especially, there are other problems that we have on the continent in general, high infant mortality rates, high under 5 mortality rates, and we cannot address those without looking at the population of children and people with rare diseases. Like I said, all of them, most of them, 98% of them, still undiagnosed. And so I'd like to tell you a little story of another out of Africa experience, which is my experience. Moving from South Africa and practicing and researching on 3 other continents, I left South Africa as a clinician and I returned as a clinician scientist. And so it was out of Africa. I came back with a rucksack full of skills and ideas on how we can address the disparity between what I was used to in Germany, in Denmark, very used to at Boston Children's Hospital in the United States, and how we could do this in Africa, at the very tip of Africa. And so back to these cute little ones. Ben, any ideas? So I start the ones that I thought would be easy maybe to have a clinical diagnosis for. And that's where we've been for the last 20 years of doing clinical genetics in South Africa and on the continent. We were left with a clinical differential diagnosis. You need to take that a step further. You need to know exactly what the gene is, and you need to know exactly what the variant is to get a definitive diagnosis for these children. And so I think only the baby in the bottom left with albinism is probably the only one that I can make a spot diagnosis, and I can tell you exactly what the underlying genetic fault is to the variant level. But the rest of them, we have good ideas, but no definitive diagnosis. And so the obvious thing was to establish an undiagnosed disease program in South Africa and try and get them tested and get them diagnosed. Excuse me, right. So you do something for the first time anyway, it's hard. You do something for the first time in sub-Saharan Africa, it's harder. I was told by many funders and many also well-wishing people that maybe genomics is not a priority for Africa. They didn't qualify that very well to say that, maybe rare disease genomics is not a priority for Africa, because as we've learned, pathogen genomics is taken off across the continent really nicely, and we're going to be dovetailing on that, which I'll tell you about a little later. But we also heard things like, this is too difficult to do in Africa. The population is so understudied and so complex, like this is not going to be worthwhile, especially not in the near future. And I agreed with some of the criticism that, yes, it requires specialized infrastructure. That's true everywhere. The necessary skills were still lacking, but we have plans in order to address those. So I thought, this is not such a big deal. What I did not enjoy hearing was that they said that Africans would not be able to understand genomics, or that they would be less interested than the rest of the world. You'll see how that is turned out to be untrue. And the last thing was, maybe this is too early for Africa. And if you take it in the context that we're already 10 to 15 years behind the rest of the world, my question was, how long would you like me to wait? Should I wait 5 years or 10 years so that in genetics terms we're 50 years behind or 100 years behind the rest of the world? And my answer was, English, there's no time like the present. And so we forged ahead, and within 6 months I was able to get the test, the machine, train the team, and get us to get our first patients to go from being undiagnosed to diagnosed. And so too early for Africa, it went really quickly. So let's get to busting some myths. This can't be done in Africa. And I was like, we have to prove them wrong. This can so totally be done in Africa. We had a shoestring budget. We didn't have many skills at the beginning, but that happened quite quickly to be able to develop the skills. I phoned many a friend, so who wants to be a millionaire, you phone a friend. I found many friends with local and international collaborations, and we were able to, within, like I said, 6 months, start to do this work. And so the old English adage of where there's a will, there's a way, it really holds true in this case. The will was very strong. The second myth was that Africans couldn't be bothered. So why should we bother? Actually, 99%, and I think that's 99.99999 at the moment, because out of 700 and some odd families, only one has said they're not interested in research, but not interested in research at all, not interested in research at this point. And so, you know, but they are scrambling to getting access to research, to getting access to testing. We've prioritized Maggie, so the Simpsons are my favorite family. We've prioritized little ones like Maggie to get access to the treats first, to the testing, but families are clamoring amongst themselves and between themselves to get access to this. They are very much able to provide informed consent. They are very able to understand the test results. If you look on TikTok, there's a granny whose granddaughter has a very rare skeletal dysplasia, and she does TikTok videos to explain to you know, the rest of the world what's going on, not only about the clinical aspects or the social aspects, but about the genetics and the testing. And families in general are really interested in data sharing, and that's been really interesting and also challenging for us to see how we were going to implement that. And so we have to bust this myth to say, yes, they are very eager to partake in research. We had a fear that too much diversity would hinder success, and so an undiagnosed disease program by definition is not, you know, just concentrated on one particular disorder. So we didn't just look at hearing loss or kidney diseases. We looked at everything, the diversity that is in the clinic amongst all ethnicities, all ages, although we did prioritize children. Our populations are 99% non-consanguineous, and we hardly ever have access to a trio. So this was mainly singleton exomes that we were doing, and just recently published a paper that says that the diagnostic yield is about half. So the diversity was there, the diversity is interesting in the results you can see, but it didn't hinder us from providing half of the patients that we've tested thus far with a diagnosis. Another myth was that maybe there's nothing new to learn from African patients. Whether you are Felicia or Lundanele, who are the 20th and 13th patients in the world diagnosed with their particular disorders in the top, or whether you have a more common disorder like Noonan syndrome or Rubinstein-Taybi, there's so much more we can learn from these patients about natural history, the mutational spectra of diseases. We can put them into just Gestalt Matcher database and see how that contributes. There's a lot that Africans can bring to the party, not only to benefit us, but to benefit the rest of the world. And if you're looking for a new gene, I suggest you come and visit us, because there's lots of potential for novel gene discovery. And so Africans in general, especially in the rare disease space, have loads to contribute to the rest of the world. We do live in a resource constrained environment, so even if there are approved therapies, our patients will likely in the short term not have access to them, so we can't even offer the SMA drug. But just because you can't treat it, why even try, was the question. The definitive diagnosis has value in and of itself. Value on a scientific basis, but also value for the family in terms of empowerment, in terms of relief. Can you imagine sitting there with a mother who says after 21 years, finally hearing the diagnosis, that, oh my goodness, for the last 21 years, I thought it was the cheese that I'd eaten during the pregnancy, and now we have a diagnosis. And they can go onto Facebook and get access to other people and find a community, and so getting the diagnosis is the first step, but it's an invaluable one. Challenges are too many to enumerate. We'd be here for the next 3 months if I was going to talk about this the whole day. Money as the source of all evil, but also the mother of all invention. Does it go like that? I think I just made that up. Is at the heart of a lot of the challenges that we face, and we can overcome many challenges with money. So if you know anybody who was really successful with crypto, please send them my way. Yeah, but also in terms of skills and education, not only on the scientific side or the medical side, but also in terms of the general population, understanding what's genomics. COVID has helped us a lot with that, so people know what mRNA is and they know what sequencing is. So that's helped, but there's a lot to do. There's very little buy-in from stakeholders. So my hospital is the only one in the country that supports genomic testing. That needs to filter out and get out, not only in South Africa, but at university hospitals, at least in the rest of the continent. We have problems with data sharing. We live and work in silos, so even if I'm doing testing in my hospital, I can't data share with the hospital down the road. and we need to address those kinds of challenges. And then importantly, we are very underrepresented in terms of global genomics. And so this picture has nothing to do with genetics, but I like it. It's a representation of GDP like 12 years back. And if you think of the world as balloons or continents as balloons, you can see that Africa's literally had the life sucked out of it. And if you think about that 3% of GWAS studies include African patients. We use Nomad on a daily basis. How many Africans are in that big database? So if it's not in Nomad, it doesn't really mean much to me as a clinician. And representation does matter because data inequities and data disparities really do mean directly health disparities, and we have to ask, where's the equity? Finally getting to the triumphs. We don't want to spend too much time on the challenges. Everybody will get bored. Bart's my favorite patient, like I said. Getting an answer for him has far-reaching consequences, not only for him, but for his family, for understanding the underlying biology and pathophysiology, and also for getting families access to other families and support groups, which is invaluable and something that we as clinicians and researchers often neglect because we only see them for 1 hour a day, and for 23 hours a day, they live in a community and need support in a different way. We've been able to train and upskill many, many young people in terms of very rare skills like bioinformatics and clinical genetics. And this is filtered out not only to my group or our country, but further into Africa. We've been able to improve variant interpretation on the continent. We've expanded the phenotypic information and understanding of many different disorders. There's active translation going on. So Alexei, you know what they have? They've got, all these patients have Mabry syndrome due to a founder effect variant in PGAP3, and that has been translated into an easy, cheap, quick diagnostic test, and moving from 6 or 8 patients, now many more dozens across the country have access to a diagnosis. And there are new projects with new genes and other things that we are able to explore based on just the first 2 years of the undiagnosed disease program. I'm very blessed to be able to work on a Tygerberg genome campus. So the brown building is Tygerberg Hospital. It's very much a 1970s building from inside and out, but we're able to do genomics there and good clinical genetics. My lab is based in the BMRI, which is the building on the left, and we have support in terms of 2 NovaSeq 6000s, a couple of NextSeqs. Also on the campus is this SAMRC Genome Center. They've got MGI infrastructure, and so we're really building a hub for genomics at the southernmost point of Africa that can serve as a hub to support activities in the rest of Southern Africa. Oops. The stars indicate where there's some clinical genetics going on, some research going on. We've learned from COVID that we can work very well together, and getting samples and data and working together across Africa, we can actually really get close to doing everything in Africa by Africans and for our population. Who's seen a telephone like this? So, yay! If I ask that question to young people in Africa, people would be like, what's that? Maybe in the internet or in the old movies they've seen it. We hardly ever had like landline telephones. And so, you'd be hard-pressed to be able to identify what that was. But everybody, almost everybody, has a smartphone. Some of us have 2. And so, we've jumped over having landlines straight to the new technology. And this is indicative in genetics for, variant testing, single gene testing, etc. We're going to jump over all of that and go straight to whole genome. And that's going to be available from 2023. The next frontier also needs us to think a little bit more creatively and a little bit more openly. And so, the man being snowed under with bureaucracy, nobody in Africa has seen a fax machine for the last 20 years. We don't know what checks are, so it's a culture shock moving to the United States and having to work with checks. We have less of those types of challenges, and so I think we'd be able to move on to adopting and being early adopters of some newer and novel solutions because we have less or fewer of the older solutions. It's an exciting time to be in Africa. You should come and join. And so let me see if this is going to work. Yeah. So I'd like to thank everybody, especially the AGD, for the kind invitation, and my team who's watching, everybody's watching at home. Hi, guys. Everybody in the collaboration and everybody who's listened to me talking about some of the work that we're doing in Africa. And I'm very happy to take some questions.
Wow, that was amazing. I'm awestruck. So I mean, there's plenty of questions. Let's start with the people in the audience, please.
Thank you so much, Shahida, for such a beautiful talk. I will just give you a standing ovation for what you have started in South Africa from scratch. That is brilliant. And as you said that there is no genetic information on nomad from Africa. So I was wondering that the variants in Africa, if you find a pathogenic variant and you see that variant as a polymorphism in the other populations, so how would you decide to work with that variant further? And that information from Africa would also influence on the already existing variants identified in European or Asian populations.
Exactly. So, like I said, there's lots to learn, and we do need information not only on pathogenic variants, but on polymorphisms that are very common in our populations in order to do variant interpretation more correctly. There are several variants that I can think of off the top of my head that, according to ACMG classification, are likely pathogenic or pathogenic. We know that they are not because we have a database of now over 300 patients that we've done exome sequencing on, and we see them in healthy adults or healthy parents, and in other patients that have totally different syndromes. And so having a local database and being able to access that is invaluable in the way that we are able to do clinical variant interpretation on a daily basis. We can't necessarily rely on all the things that are available in the global community, and need to have some local solutions for being able to do our work in the best way.
Thank you, Shahida. I have many questions, but let's move to the next.
Thanks. That was a terrific talk. You mentioned, and I was wondering if you could just talk a little more about the successes you've had with training and employing bioinformaticists. Could you just talk a little bit more about what's worked, what hasn't worked, and kind of future plans in that area? I think we're all excited about that area, but I'd just love to learn more.
So bioinformatics is really one of the very rare skills on the continent. So you can get real experts in bioinformatics as far as COVID is concerned, and they've really shown, by publication and the work they've done in the last 2 years. But bridging the gap and coming to rare diseases, it's been hard for me to find a postdoc, for example. So we've started really from honors students, so BSc honors in the 4th year of BSc, and master students, and training them to be able to do the bioinformatic and set up the bioinformatic pipelines necessary. And so, we've got a few master students that are working currently and becoming bioinformaticians that will go on to PhD. So at the moment, what they're doing is basically just optimizing pipelines that would be clinically relevant for us. And then in PhD, going on and moving on to trying to find novel solutions, novel tools that would be helpful for us in a clinical space and in a research space. And so those are what we're thinking about going forward. At the moment, it's just been about optimizing and finding something that can help us to drive the work forward, and innovation is coming.
In the front. There's the cube on the way.
Whoops.
First of all, thank you for this beautiful contribution.
Thank you.
On one of your slides, you made a brief mention of consanguinity. And it appears that you wish to play that factor low, maybe unintentionally or intentionally. That is exactly my question. Couldn't that be a chance for Africa, where are huge subpopulations which practice a high degree of consanguinity. The consanguinity belts are located across sub-Saharan Africa. And couldn't it be that it is a special chance we don't have in Europe and we don't have in the US? And think about the huge contributions through the last, say, 5 years or so, which were made from Arabia, in that could be a special chance for Africa as well.
Yes, oh, definitely. So we see in several subpopulations across the continent where consanguinity is high, not comparable to Turkey or Saudi Arabia, but there are many populations that have higher consanguinity than others. They're easier to test, they're easier to find, to diagnose, and they're easier to explore in terms of novel gene discovery. And they hold a lot of promise for trying to find new things in those populations. The point I was trying to make was that it would not be as straightforward in our population because they're not consanguineous. And non-consanguineous families are sometimes difficult to study, especially in the absence of having access to all three, mom, dad, and the affected person.
Question from Peter.
Yeah, we often complain about GDPR, but actually it was intended to facilitate data sharing in Europe. Yeah. So how does that work in Africa across the borders?
We have very specific data protection or people health information protection laws that differ from country to country. We haven't explored yet exactly what that means for genetic information. And it really depends at the moment on our university or IRB. And that causes trouble when we want to share data between two different centers, even in the same city. So we need broader solutions in order to get past those silos that we work in and individualized sort of rules that we have. Our broad rules don't necessarily apply to specific things like genomic data.
So I think we have time for 2 more questions.
I will speak longer than what I planned to, faster than what I planned to.
No worries. Yes.
Thank you very much. This was very inspiring to see. I know that's a huge work and probably also frustration from day to day. But I think keep going. This
Thank you.
The question you made a very important point to say like Africa is not Africa, and the diversity. From some initial studies, it's clear that the diversity is almost extreme compared to the rest of the world. So. And you're having this nice conference now, but is there beyond that, between different countries, like ideas, networks, funding, or even if it's only ideas to how to tackle that? And there's the daily business that you have to do locally, but do you think there's a chance to also bring again others from other continents in there? Because my experience was, for example, with Tanzania. A very big border now was, when it comes to data, is that data is recognized in Africa very well as a value. I had the feeling even more than it's here. Yeah, it's like we're not giving it away because we gave a lot away in the past, and this is not going to happen again. Yeah, so this combination of you need to work together between the countries, but yet everything you generate is of huge value and might want to be protected even further.
Yeah, that's an important point. So we have a bad history of helicopter science, so people flying in, collecting samples and leaving. That's, has left scars on the entire continent, especially as far as genetics is concerned, because the populations who were exploited never gained anything from what was done. I mean, even in terms of publication, there was never ever an African person on the publication. And in terms of clinical genomics, those families never got the answers. So they were published, but there was never ever results delivery. And so, there are scars that need to be overcome and need to heal, and we need to build up more trust in the populations. It seems that within the continent, there are plans. So there's an African Society of Human Genetics, and we're working towards getting funding to do our own version of NOMAD. You know, it's going to be a bit more complicated, but we need to do this. And, you know, versions of like Genome DE or 100,000 UK Biobank, those types of things need to happen in Africa as well. There are plans. It's always just a matter of the money and the investment and the buy-in from those to see that this is an important step that we need to take.
Thank you again. Next up, we have the final speaker of this session, Ben Solomon, the clinical director of the National Human Genome Research Institute in the United States of America. He's going to talk about the educational value of style GANs.
All right, and to start, I have no idea how to get my presentation, so I'm doing well here.
Clinical director, right?
Right, exactly, yeah. Not computational, right? Next lifetime.
Do you remember the file name?
It should say AGD something Solomon. Oh, there it is. 2 down from the last one.
Yeah, sure.
All right, perfect. So that is a tough act to follow. If I were back home in the United States, as Peter knows, I tend to talk so fast, you guys would get to lunch early, but I'm going to try to go a little bit slower than usual. You'll notice I changed my title of my talk from what's in the program, but I'm going to talk about GANs. I'll explain them much worse than Fabio did, or I'll talk about them in a much less intelligent way, but I'm going to talk about how we educate both the computer and the clinician. So the talk is divided into 2 halves. The first half is intended to make the clinical audience think that I don't know anything about clinical genetics, which is kind of true. The second part is to prove to the computer scientists that I know nothing about computer science, so I'm going to leave everybody unhappy. More importantly, I wanted to just highlight my small but mighty team. There are a couple people missing, but we have a good and relatively newly formed team working on some of these areas. So to start, just background in philosophy, I should also mention I have lots of, I'm glad Shahida did the same thing. I have lots of cartoons in here. In the United States, especially within the last 3 years, I teach a lot on Zoom. I think everybody's asleep, so I do everything I can to keep people at least paying attention a little bit. So this is the clinical part, and I can just speak for where I am from, the United States. We don't have nearly enough geneticists for lots of reasons. You can see they tend to be concentrated where the big academic medical centers are. So in red, that's where there are geneticists, physician geneticists like me. In black, that's where they are trying to hire more clinician geneticists. And then you can see in some parts of the country, they've just kind of given up. They say, forget it, we're not even gonna try. The other point I guess I would try to make along those lines is that, and this is a terrible graph, it's probably not accurate, this is just me just Googling all these things, but it's probably kind of hazily okay. There's only a couple thousand geneticists, and most of them, like me, aren't helping at all. I'm not really seeing that many patients. I'm mostly here doing research. There's lots of other types of clinicians, and I would argue that the way that all the great tools we've heard about in the last couple of days, where they're going to make their most impact, isn't with people like me who aren't really helping anybody or seeing that many patients, but it's the pediatricians, the family practitioners, the cardiologists who could probably most benefit from some of these tools. So same trend in terms of distribution, but worldwide with genetic counselors. The theme is that there's a lot in some places and less in others. What's really interesting, at least in the United States, is there's been this big boom of genetic counselors over the last 5 years, mostly because of diagnostic labs doing really well. That kind of ended, sadly, for a lot of reasons, and so we'll see what happens. But we sadly have not seen more physician geneticists. Maybe they meet people like me and say, I'm going into cardiology, but it's been pretty flat. So going back to one of the themes of the conference, artificial intelligence and deep learning, this is from just a little review paper we did. We can see that the applications of these tools are focused both where the authors are and where the data is from in certain countries. And to Shahida's a number of the points, clearly doing a better job of this would help everybody. Just to demonstrate just some of those points with a little paper that we did. I think this is, we needed, I should have called this Skin to Genes, so I could have gotten into a better journal. This is a good journal, but I mean, you know, help the impact factor, I guess I shouldn't have said that. But we did one of the introductory projects, kind of like was said, just to build up our pipelines, we did on skin images. So we looked at both the kind of pictures, you know, that mom or dad might take with their phone, and then zoomed in pictures. And we just looked at a number of different genetic conditions and said, how well can a classifier do versus geneticists like me or a pediatrician down here. Whoops, I'm not pointing really well, down at the bottom. So the red dotted line, that's how well our classifier did. And each dot is a different person. So some people did really well. Most people did not do nearly as well as the classifier. As an aside, one of the things that we're working on now through some algorithmic approaches is taking the people that were really good, I was not one of those people, but the people that are really good, and seeing if the AI or the classifier can learn from them specifically. But the point, again, I just wanted to make is that the pediatricians, these are the folks that are seeing most of the patients. They're you know, geneticists in the United States, there's a 6-month wait time to see one. At a lot of places, there aren't geneticists. So the more we can get the great tools that you guys build in those hands, I think that's where it's going to have the most impact. So again, this is just more philosophy. One of the things that when I teach residents and fellows, they still let me do that, is I talk about the past. And again, Shahida had some slides that showed this really well. You know, a patient would come to me and I would say, I would try to pretend I'm really smart, say, okay, let's do some x-rays maybe, and I don't know, just some general blood and urine testing. I wouldn't get an answer, I'd do a karyotype. I wouldn't get an answer, then gene 1, gene 2, microarray, research referral, et cetera, et cetera. So I think everybody knows this. There's lots of exomes and genomes going around. But the point that I wanted to make, and it was great to see, for example, Nicholas's talk on this made this point better than I will, is what I try to teach now is to say, okay, is it genetic or is it not genetic? That's the first branch point. And then secondly, the thing that I feel like we all forget, at least speaking for me and my colleagues back home, is not just what is the molecular diagnosis, but what at that point is going to be the thing I can do to take care of that patient, right? Because it might be order a panel and get your results back in 2 months, but you've missed a lot of time to actually clinically do what's right here. So just as an example, if someone like this were to come into, for those, I don't know who are clinicians here, but let's say you're a clinician, someone like this comes into your clinic, you're going to immediately say, that's interesting, but what's really interesting is looking at that person's heart right now before I get sequencing back or any kind of molecular test back to make sure that I'm taking care of that person's cardiovascular system, because that's what's going to kill them. So that's an obvious one. This is maybe a less obvious one, and either Gestalt Matcher or some of the clinicians will be able to diagnose this patient. I always think of this condition because I got yelled at so much when I was a fellow for missing a patient with this condition, for missing this diagnosis. This is Williams syndrome. One of the hints is kind of the puffiness under the eyes, but these patients also can have, because of a change in the elastin gene, that they're missing that, they can also have cardiovascular anomalies. So same thing for this kid, we want to look at this kid's heart. And then another kid, and I picked out this condition because this is not a diagnosis you would just get from a genome or an exome. You'd have to be suspicious and order a specific test, but I'd want to start checking that kid at a certain age for risks of cancer, right? Because they can have occult cancer that I don't want to miss. So the point what I'm trying to teach, and the point that I guess when we work on these AI algorithms, is to work on diagnosis, but also what's the management step that would go along with the suspicion of a certain condition. All right, so that's it for philosophy, I guess, on clinical stuff. This is more philosophy on science, and sorry for all the bad jokes. All right, so we heard a lot about GANs already. I'll maybe touch on a few aspects, but again, Fabio explained this much better than I. Going back to that skin condition paper, one of the things, and when we were working on this, I hadn't really even thought about doing this, but one of the computer scientists in our group said, oh yeah, we can do this, isn't this fun? So these are all fake images on the top of neurofibromatosis type 1, kind of the birthmarks that a baby would have. On the bottom, another condition. The bottom condition is also important just clinically, because that's where I think a lot, because these folks are at risk of certain types of cancer and other endocrine issues. So they look real, you know, a clinician can't tell them apart from a real one. One of the nice things that you can hint at here, or that you might be thinking of here, and I'll talk a little bit later, is that you can see that there's different skin types, different skin colors. So as was talked about in some of the earlier presentations, you can intentionally alter things. I'll talk about why you have to be careful with that, but you can make the data set more diverse so you're not just recognizing a condition in a certain population. Just clinically, again, part of the reason it's good to be able to recognize these well is because this is just a graph of neurofibromatosis type 1. When kids are born, that's often the only sign that they have that's obvious for this condition. It's not till later that some of the other findings pop up. So as just kind of a fun proof of principle, what we did, these again are all just GAN-generated fake images of someone's back, not a real person's back, but this is just an image of disease progression. So you start with just these cafe au lait macules, these birthmarks, and then you get some of the other findings that come with time. So this can be nice for, as you can imagine, a variety of reasons, predicting prognosis or predicting prognosis to a therapy. One of my colleagues works on a rare genetic condition called Proteus syndrome and is testing a medicine to remove some of the skin lesions. And so we can apply methods to treatment trials in a similar way. I won't explain this again, so you won't insult me too much, but I think that was left to one of the previous talks, but just a cartoon that I like to show kind of how a GAN works. Again, to get you guys to lunch, let's skip it. So I'll give you guys a second. This is, again, I do lots of examples with Williams syndrome because I'll never forget getting yelled at for missing that diagnosis. So these are 5 people, some of whom are real, some of whom aren't real, of GANs of people with Williams syndrome. So take a second, or I'll give you guys 30 seconds and decide which ones are real in your head. You don't have to yell it out, but just in your heads, which ones are real and which ones are fake. We should have like those little, I guess, Jeopardy or the countdown thing or something like that. But all right, so these are the 2 fake ones. The others are real. This was just a quick thing that we did. You could make these pictures much higher resolution or much more perfect. Those of you who are familiar with this, probably my guess is some of you guys got this immediately because you look for hints that are sometimes weird in GANs, like little things with the hair, sometimes asymmetry with the ears and things like that. So some of you guys may have got that. We'll talk a little bit more about that, but these are things that are fixable. But it's interesting just seeing the things that the computer kind of gets confused at if you're not careful and fine-tune things. Oh, whoops! I put this in late, so let's see if this works. One of the questions, I don't know if he's still here, but Dennis had asked earlier, is about how these GANs can be used, and Nicholas talked about this too, in a model with aging specifically. So let's see if this disappears. Oh, nope, I disappeared the wrong one. Okay, forget it. I'll try to show you later, but what this shows at the top this is someone with, I think it was Williams syndrome in this case again, and we showed how they would age. So we took a GAN and we aged that picture. And the top is, I think, an older person, the bottom is a younger person, just to show how that would progress. That's important for a couple of reasons. One is most geneticists are pediatricians. So I'm pretty good at recognizing syndromes in young kids. I'm supposed to be able to recognize those same conditions in adults, but I'm not very good at it, I'll be honest with you. And most geneticists are similar to me, aren't adult trained. So generating more images to show that can be helpful for education, again, getting back to the theme. And then, to Nicholas, to some of the points that you made, when we fed these back into the classifier, they do boost performance a little bit. So if you use GANs in perhaps some of these clever ways or trying to think about how it would work, they can help. And again, to, I guess, Dennis's question earlier, you do see that the classifier is better or worse at certain ages. And I'm sorry that I messed up the animation on this. If you guys are really interested, I think it's in that, this picture is in that article. Let's see. All right, so I just wanted to mention this just because we've seen tons of stuff in the news about DALL-E and these diffusion models, and so they're super fun. My kids and I, we have it on our phones now, and we send their best ones to each other. So this is the NIH Clinical Center. That's where I work, in the style of Van Gogh. A couple of them are good. Most of them actually look like the main NIH building, not the building where I work. So the point is they can do these fun things, but they're not really accurate. For example, currently, just with the, the open models now. So if I type in, kid with Williams syndrome, I'm going to get something that does not look good, or you name your syndrome, or it doesn't work well. But of course, and I think someone from Peter's group put this on our group chat or whatever we call it. Again, I'm showing that I'm not that computationally as good as I should be. But if you just fine-tune the model, if you feed in a lot of data using diffusion models, you can do the same thing. You can make highly accurate images, and this was one of brain MRIs that they used. What was interesting is in the discussion they said, oh, these could be used for retraining models. The problem is as we've seen, they're not necessarily helpful unless you do something clever or different with them. They just kind of it's circular logic. But you can make pretty pictures, and that's kind of a good thing by itself. Again, when you test clinicians on these, clinicians can't tell the real from the fake for the most part. So some colleagues at the National Eye Institute did this study. These are just different eyes, and ophthalmologists can't tell what's real from what's not real for these. This was a New York Times article from maybe a year or two ago. And again, I'll give you a second look at these ones, and I bet you can figure out which ones. These are all fake. But which ones kind of are bad fakes or are detectable fakes? So look for a second to see if you can figure out one or two. And again, you can fine tune, you can fix these things. But some of the things that I tend to look for: earrings, so asymmetry with earrings. It'll often do that. Asymmetry with glasses, and occasionally, though the models are better, just weird things with hair, like a chunk of hair kind of floating in midair, or things like that. And again, going back to genetic syndromes, we've actually, and Peter's group, who we meet with sometimes, will show you this, but one of the things that you get into trouble with is you try to take a real image. This is someone with Angelman syndrome, and you say, I'm going to alter that image, and you just do kind of some of the easy publicly available stuff. You get an image that looks like this person, but you lose a lot of the syndromic characteristics. So we're actually, I think I don't want to say we've solved this, because I know that's very specific, but we're a lot better than this. This was an early one I showed, just showing the problems that you can run into with some of this. So clinical education, at least for me, when I was training, someone would say, hey, we're going to go see a patient with Angelman syndrome or Noonan syndrome. And what we would do is we would usually go to this book. I think I would go to, this is the 8th edition. I think I had the 5th edition when I was training. But anyway, we'd open it up and there'd be 1 or 2 pages of black and white and color pictures, and we'd look at it, and you'd see 5 pictures and say, okay, I think I might recognize those. So one of the things that we've done, and this is just making more data for people to look at, is making more and more diverse data sets for students to look at. And I'll show you some of the ways we're testing if these work or not. So these are all fake images of people with Kabuki syndrome, who I think look pretty realistic. More importantly, we fed them through our own classifier and a much bigger and better classifier that you may have heard of over the last 2 days, Gestalt Matcher, and they seem to work pretty well. Again, you have to be careful, and we're grateful to your group for picking out which are overlapping images between our data set and your data set, but overall they seem to be working pretty well. In the United States, at least, and I think probably everywhere, using these fake images in various ways can help a lot with privacy. There's a lot of concerns about data sharing. I've heard a lot over the last couple of days about countries where data sharing is not as problematic, maybe like Israel, and there's different beliefs in Germany. United States probably in the middle, but I'll be careful how I say this because this is recorded. I would say because of some of the polarization in the United States, there's less trust of government handling data, and I'll just leave it at that. And in the coffee break, we can talk more about issues with that. But in any case, one of the PHI data points that we have to be very careful, even where we do the analysis has to do with facial photos. Also, by the way, retinal images, but not certain types of eye images. So there's certain permutations we have to do. But this can help a lot. Maybe it's not as cool as swarm learning, but it can help with some of the data sharing stuff. Going back to one of the themes I talked about, one of the ways that this can help is representing more diverse data sets. But again, you have to be really careful and not do this quickly. But just a story, you're wondering why I'm showing this map. So I trained in pediatrics and genetics near Washington, D.C. That hospital there, I trained at Children's National, which is just a pediatric hospital. it didn't have a labor and delivery center, so we had to get trained to, take care of zillions of babies. So this is one of the busiest, this is one of the busiest hospitals in the area. It's in Maryland, just north of DC, called Holy Cross Hospital. And when I was there as training as a resident, I talked to some of the attendings there, and they told me some interesting stories about genetics, because they knew I was going into genetics. And starting about 20 years before that, there was this huge wave of immigrants and refugees from Central America because of the civil wars and other unrest there. So a lot of people came to that Washington, D.C. area. And so a lot of the attendings told me that, they were pretty good. They didn't have geneticists. They were pretty good dysmorphologists with their population. But as soon as these other populations started moving up, they felt much less comfortable, knowing if a person or suspecting if a person had a genetic condition or not. We see the same thing with, some of the classifiers that we've done. Cedric recently took his first post-training job, but he's the first author of this paper I wasn't involved in. But you can see this is Rubinstein-Taybi syndrome, that the models perform not as well for people of African descent as other descents. I think we and others have shown that this mostly having to do with what's in the data set that you're training on, right? So if you have not very many people in that from that ancestry in your data set, it's not going to work well. It seems really obvious, but the numbers bear it out. So one of the things, again, this is just early things that we've been playing with is, how do we make more diverse images? But you have to be really careful about that. You can't just take someone, say, from Germany with Rubinstein-Taybi syndrome and say, we're just going to change your skin color, and then we're going to assume that that's how a person from a culture with a different skin color would look, right? As I think a lot of the posters went into really nicely, there are lots of specific attributes that we have to be careful with. But there are ways that we can very carefully weight our data sets or collect more data and generate more accurate and more diverse images that will help make these tools work better and more equitably for larger groups of the world. Okay, now a little bit about using GANs to improve classifiers. So Nicholas, this one's for you. Not what the images are, but just reminds me of your talk. This was a study that was published a few years ago where they said, okay, can we teach the classifier to recognize broken bones? These are femur fractures. Let's generate with a GAN a lot more femur fractures, and let's feed them back in. And as you heard, it didn't really work. It's just kind of circular logic. More data made of your data doesn't really help. This was a pretty big data set, and other data sets have shown similar things with similar situations. We did a paper, and again, we tried to be a little bit clever, and I think it helped a little bit. It probably helped us that we were working with rare diseases. This is a class of genetic conditions that involve albinism. And so people with albinism, as you can see, their skin is lighter. They also have differences in development in the back of their eyes, so their vision's also often affected. It's called foveal hypoplasia. And some of you, I'm sure, know much more than I do about this. Traditionally, what happens is you get an OCT scan, and an ophthalmologist grades what degree of foveal hypoplasia you have, and that would be important because mom or dad wants to know, hey, can my kid, will she be able to ride a bike when she's older? Will she be able to drive a car? What's her vision going to be like? And so some of these types of scoring systems give you some of that information. So we did a classifier with about 400 OCT scans from people with these types of conditions. We tried different things with different types of data feeding into it, but the interesting thing was that we generated with this version of StyleGAN 2. Oh, this is a good one, by the way, because it's adjusted. It works well for small data sets. So for rare diseases, this version of StyleGAN seemed to work better for us than and for other studies than the regular StyleGAN 2. So we fed them back in, and hopefully this one works. Oh yeah, this one works. So it's not like this dramatic, oh my gosh, 30% better, but you get a few percentage point improvements when you're feeding in these different GANs into the classifier. What was interesting though is that what it seemed to work best at, and I thought this was kind of another little trick that might be applicable, is if something's an obvious, let's say grade 1 or an obvious grade 5, it doesn't really help. But there's ones that are right on the border. Is this a 3 or a 4? Is this a 1 or a 2? And so we made these mixed ones where we mixed them grade 1 and grade 2, and it seemed to help with some of those, I'm using the wrong word here, edge cases, but I guess difficult decision cases. It seemed to help most with those when we just manually looked at the results. So from that, and this is going to seem really stupid and weird, but from that, what we did, we said, if it's teaching the computer to do that, maybe this could be something that could help clinicians as well. So this would never happen in real life, right? So this is a fake person, a GAN-generated, unaffected person, and so we're turning them into someone with Kabuki syndrome. So this person is 25% Kabuki syndrome, 50%, 75%, and then Kabuki syndrome. Same thing with Noonan syndrome. So it's not going to happen in real life, right? But what we thought maybe it could do is it could teach a trainee to be able to recognize some of the features a little bit better, right? Because you can see, okay, what are the important features? And this is, I guess, explainable human intelligence or something. Again, I want to go back to that point I made. We intentionally chose some conditions where the clinical impact is really important. For example, in Noonan syndrome, I want to diagnose those patients soon because they could have bleeding and clotting problems if they're born with a heart defect. We want to know, the surgeon, I don't need to know about that, but the surgeon needs to know about that. They can have heart issues and other things that are important to know about before the, in most cases, weeks to months before we get a sequencing result back. So Amna Othman, who's a fellow that's working with our group now, has done a lot of this work and is continuing to lead a lot of this work. This is just a beta testing example with some of those strips. So basically, do those strips help? Totally anecdotal, N of 1, but we see the same thing in N of 5 or 6, is that this is pre-test. Then we show them these GAN strips, we call them, and this is post-test. They seem to do a little bit better. So we have lots of surveys going out now to pediatric residents, because we think that's the sweet spot where they may have heard of this condition, but they won't be able to recognize it yet, to see if this helps. And does this help more than just showing them real pictures, or does this help more than showing them a bunch of fake pictures without the transformations? So we'll see. Another thing that helped me a lot, and I'm much better at recognizing these conditions than I used to be because of playing with them a lot. This is 22q11.2 deletion syndrome, or sometimes called the George syndrome. But this is a Google Colab that we made where you can change, the age and other parameters around it, and it'll just keep generating these strips for you over and over and over. Zung, I don't know if you're taking a picture, but I don't think the link still works right now, or maybe it's not on there, so we have to fix it. But we generated lots of these. You can just press the button, generate another, and press a button. And you can change the parameters, but it's going to be relatively random based on a lot of things like where the patient is from and things like that. So it can help just let you see lots and lots of these images. Oh, sorry, that's where you change something, I think. And then lastly, and I promise I will finish on time, one of the things that we're working with now, and this is back to that same image of Angelman syndrome, to look at kind of what could be confounders, is we're playing with these images. This is another fake image of a girl with Angelman syndrome, but we're changing the expression and seeing, for example, if some of the things that are stereotypical about Angelman syndrome, like a smile, if we change that smile, how does a computer classifier work differently? How does a person work differently? How do they look at the image differently with things like eye tracking? And so that's a next step in our experiments. So with that, I'd like to thank you and finish on time. Again, huge thanks to the group, including folks here and others that we've collaborated with. Thanks.
Thank you for your great talk and introduction on how this can be used for education on multiple levels. Are there any questions from the audience? Let's get the cubes going, guys. Come on. Let's start with Fabio.
You're going to ask me a really hard one about coding, aren't you?
No. Actually, I just have a very simple question regarding the style GAN that you used. Did you generate those synthesized faces in the process, or did you use those as an input and then modify them during the style GAN process?
You mean during the quiz or whatever that we're asking people during this? During this kind of test?
No, in general for the style GAN, where you transfer the healthy face to a non-healthy face.
Yep.
Did you synthesize those phases in the process as well?
Yeah, we did both, and but I will say this is we've tried both. We've tried lots of different versions and iterations. We're still very much in the process of fine-tuning this, so and looking at parameters and testing it with different classifiers and saliency maps and you name it. I would say we're happy with it now. Not yet finished though doing it, but yeah, we're testing lots of different things there.
Okay.
And if you have hints for better ways to do it and things to do, I'd be happy to hear perhaps in the coffee break.
Yeah, thank you.
Yeah.
Yeah, thank you, Raj. This is fascinating. Question is, do you have any of the syndromes where it's known when you look at old textbooks from the 1950s or so and look now that the phenotype has changed, because of environmental changes and lifestyle and so on? And would you then expect that you have model shifts? And how would you address that?
Yeah, it's a terrific question. We haven't asked exactly that question, but one thing that's pretty clear from images that we collect and look at is, let's say you go back to the first 10 years after a condition was named, or maybe it was just clinically figured out. You tend to have, not that this is clinically real, but it's an ascertainment bias, you tend to have much more severe images of those folks. So people assume that that is a much more severe condition. Now we tend to get a much more representative sample, but it's still probably skewed a lot towards a more severe model because those are the people that are getting tested. I would hypothesize, and you can tell me if you would agree with this or not, or some of the people involved in the giant sequencing projects, as we sequence more and more people, we'll get more atypical cases and probably a milder and broader spectrum of disease. But it's a fascinating question to think about. I'll go back and I'll think about conditions that we could look at from environmental factors that could be you could look at. One example that immediately pops to mind is that now there's a lot more emphasis on people with a condition called Prader-Willi on weight control, and that seems really silly. But traditionally, I would recognize someone with Prader-Willi because I would think they would be overweight when they're older because they have hyperphagia. It's part of the syndrome. And now there's a lot more emphasis on this. So I would suspect you'd see a difference there. Yeah, it's a great question.
One more quick question, okay, and then we have to move on.
Yeah, really great. And yeah, the idea of having the sliders and seeing like how, age, ethnicity, I was thinking about for retinal images as well. That'd be really cool. Yeah, GANs, I don't know. Did you see obviously you've noticed that the girl's t-shirt changes color.
Yep.
That's quite funny. But are you worried about, I don't know what the term is, reversal attacks or whatever, if you put these things online that people try and find the original images from which they were synthesized? Like certainly for language models, like that's an issue. Like, yep. I'm just wondering if, yeah.
Yeah, no, it's a terrific question. It opens a whole can of worms. One of the things I didn't mention, though, that we're careful with is that anything that we've been using to develop the models or test, we've been doing them on publicly available images. So things that you could get from PubMed, from Google Images that are already out there. I would indeed be much more careful about doing the exact thing with a patient from clinic who hasn't consented to their data sharing, even if it's a slightly altered version of them. I think it's a very careful consideration. The other thing that we've been careful with, I guess ethically as well, and it's a slightly different vein, but taking a picture of an affected person, a real affected person, not some kind of composite image, and making them unaffected. Bioethically, it seems concerning to me, and it seems to be perhaps pejorative, but there are a lot of discussions that we've had about what data we show, what data we share. I'm a huge proponent of data sharing, but I do want to do it carefully and not to do anything that would have negative repercussions, and even where we analyze the data. And I could go on and on about NIH and US rules about that, but yeah, there's a ton of considerations. You bring up good points.
All right, then we are about to close this session. Thanks everyone again, and thanks all the speakers for their contributions and their lovely talks.